And welcome back, students. Today we are going to be talking about using the LC3. We're actually now finally getting into LC3 programming. So let's talk about solving problems using a computer. So there are various methodologies for creating computer programs that perform a desired function. Of course, all this boils down to, ultimately in the end, problem solving. How can we figure out what to tell the computer to do? A computer is a pretty stupid thing unless you actually tell it exactly what you want it to do. Now, typically this is done by converting the program statement into an algorithm using stepwise refinement, and then you convert the algorithm for our purposes into LC3 machine instruction. Then, of course, from there we go to doing debugging, which we figure out why something didn't work, and we examine registers in memory, setting breakpoints, etc. So let's just talk a little bit about what stepwise refinement is. This is also known as systematic decomposition. It starts with the problem statement. We wish to count the number of occurrences of a character in a file. The character in question is to be input from the keyboard, and the result is to be displayed on the monitor. We then decompose that task into few simpler subtasks. Decompose each subtask into smaller subtasks, and these into smaller subtasks, etc., 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 until you get to machine level. So you're breaking it down until it gets to the most simplest possible form that you can make it. For pretty much you're down there, it's like it's the add and the ors and the nots and everything else that we've seen with logic gates. So let's look at that problem statement. Now, because problem statements are written in English, they're sometimes either ambiguous or they might be incomplete, or both. So, for example, where is the file located? How big is it? And how do I know when I reached the end? You know, there's a big difference between, even if, let's say, we're looking at a Word document. You know, you're looking at a Word document that contains 5,000 words versus a Word document that contains 50,000 words. 5,000 versus 50,000 is a big difference. How should the final count be printed? Is it a decimal number? You know, if the character is a letter, should I count both the uppercase and lowercase occurrences, or are we looking at it with ASCII, where it's remember, each one is different in ASCII, upper is different from lower. How do you resolve all these issues? Well, there's two ways. First, you probably want to ask the person who wants the problem solved. And then you're going to need to make a decision about it and document it. Because, you know, the important thing about documentation is if you make a mistake with your documentation, allows you to go back and make a tweak. So there are three basic constructs, or three basic ways in order to decompose tasks, even if we're looking at the example here. All right, and of course we can break it down to the subtasks. Right, and you can look at this task, you know, subtask 1, 2. We say, well, that's sequential. You see there's a test condition. We can do true, false, and get subtask 1, 2. That's conditional. And then you have test condition down here, which is then broken down into subtasks underneath. That is an iterative. And you might be able to see it's kind of almost got a little bit of a looping behavior in it. So if true goes here, if false, it goes back down. All right. So if it's sequential, what you do is you do subtask 1 to completion, then you do subtask 2 to completion, and so on and so forth. So in this case, you're going to count and print the occurrences of a character in the file. Then you're going to get character input from a keyboard. You're going to examine the file and count the number of characters that match, then print the number to the screen. It's literally, sequential means that you're going step 1, step 2, step 3, step 4, step 5. You're just simply going through sequence. And this can be good for things that are straightforward, but if you're doing a lot of repetitive tasks over and over and over again, sequential can be a bit of a burden, because you will actually do some stuff with this and you see that it can actually be very inefficient. Conditional. All right, if a condition is true, do subtask 1. Else, do subtask 2. This is really great if you want to test to see if a thing is true or false. So test the character. If matched, increment the counter. All right. So it says, okay, file character. Test that against the input. So we're at the first character. If that's true, I'm going to increase the count by 1. If it's false, I don't care. I'm not going to do anything. And then we have iterative. Right. This is really kind of getting more to a looping count, which loops are wonderful things. We have to do a lot of things over and over and over again. So this is doing subtasks over and over as long as the test condition is true. So we check the element of the file and then count the characters matched. So we ask, are there more characters to check in the file? If true, well, we're going to check the character and then count if it matches. So if the count is true, hey, let's increase that by 1. Then we go back to the top. All right, are there more characters checked? Well, yes. So if there's more characters, we keep going until we hit where it says, no, there's no more characters in that file. So then we're done. And oftentimes these different strategies can be used in conjunction with our sequential, conditional, and iterative. So when we're talking about these different things, we're talking about problem-solving skills. And this is really when it gets down to learning to convert a problem statement to a step-by-step description of subtasks. So like a puzzle or a word problem from grammar school math. So what is the starting state of the system? What is the desired end state? How do we move from one state to another? All right, we recognize English words that correlate to 3 basic constructs. So do A, then B, that's sequential. If G, then do H, that's conditional. For each X, do Y, that's iterative. And do Z until W, that's also iterative. Now, with the LC3 and its construction and control instructions, how do we use the LC3 instructions that we've looked at before in order to encode the 3 basic constructs that we just discussed in this lesson? Well, with sequential, the instructions will naturally flow from one to another. So no special instruction is really needed to go from one sequential task to another. So it's like it executes one line of code, moves to the next line of code. Executes that line of code, it's going right to the next one. It's sequential. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until it reaches the last command. With conditional and iterative loops, you have to create special code that converts the condition into a negative, 0, or positive. So, for example, you have a condition, is R0 equal to R1? In code, we say subtract R1 from R0. If equal, the 0 bit will be set. Then we use a branch instruction to transfer control to the proper subtask. All right, we can't talk about programming, though, without talking about debugging. Now, this is saying, all right, I wrote my program, and it doesn't work. Why doesn't it work? I don't understand. Why is it not working? The code looks good, but it doesn't work. Well, now what do you need to do? So here's a real-life example. All right, you're driving around, you're lost in the city. You're like, well, I need to be able to get back to my destination. So do you just kind of drive around randomly until you hope you find where you get lost? No. Instead, you're probably going to return to a known point or pull off the side road or something and use your phone's GPS to help you re-navigate your route. In debugging, the equivalent to looking at your GPS is what's known as tracing your program. This will examine the sequence of instructions being executed. It also helps keep track of the results that are being produced. So as you're doing your different ands and nots and all that other stuff, it's going to help you keep track of that. And it's going to help compare the result from each instruction to the expected result. So if you're expecting it to, let's say, give it output, I'm going to make it really simple. Say you're expecting a output of capital A, and you got an output of capital B. You know then that means that there has to be something wrong with your program. Let's talk a little bit more about debugging operations. Typically, any debugging environment should provide the means to do the 4 things. 1, display the values of memory registers. 2, deposit values in memory and registers. 3, execute an instruction sequence in the program. And 4, stop execution when desired. In order to do a forced quit of the program so it shuts down. Now, different programming levels offer different tools. High-level languages such as C, Java, C++, C#, all of those other ones usually have source code debugging tools. Like you'll use what's called an IDE or integrated development environment that will help you not only write your code but does things like on-the-fly compiling. So if you make it like a syntax error, it'll catch it for you. For debugging at the machine level, we have simulators, so things like the LC3. We have operating system monitor tools. and in-circuit emulators, or ICE. This is plug-in hardware replacements that give instruction level control. Now, I kind of already mentioned one of these types of errors, which was a syntax error. This is typically you've made a typing error that results in an illegal operation. Alright, and when I say illegal, I don't mean it's against the law, I just mean it goes against the rules of the code language that you're working in. It's not usually an issue with machine language because almost any bit pattern corresponds to some kind of legal instruction. However, in higher level languages such as Java or C#, these are often caught during the translation from language to machine code because you're writing in words that are representing English language or something similar, and then the compiler has to change that text that you've written on your screen over into machine code that the computer can actually use. Next up is logic errors. Means your program's legal. Everything looks good. I don't see anything wrong with it, but the results don't match the problem statement. So it's going back to this. So let's just say you're doing a simple thing like finding the area, and you say, "Oh, I have a length of 10. I have a width of 2. Well, I know that 10 times 2 is 20. I run my program and I get 18. Like, wait a minute. Something's not right. So what we can do is trace the program, see what's really happening, and in order to determine how to get the proper behavior. And lastly, we have data errors. This is where the input data is different than what you expected. So often the best thing to do this is test the program with a wide variety of inputs. So for example, if someone says, please enter a number, and someone decides to be smart and they press the letter A. Well, the letter A, unless you're working with hex, but generally speaking, when we think about decimal, for most people, the letter A is not a number. It's a character. So if you try to push A through and it says please enter a number, then you want to add, multiply, divide, find the error, whatever, with that number, and now you can't. And that's because it's kind of the wrong input. Alright, I've talked about tracing the program a couple times, but let's actually look at it. What this means is that you're going to execute the program one piece at a time, examining the register and memory to see results at each step. The first way to do this is what's called single stepping. In order to execute one instruction at a time. This is very tedious because you're literally going each line of code at a time. But it can be very useful to help you verify every single step of your program. Conversely, you can use what are known as breakpoints. This will tell the simulator to stop executing when it reaches a specific instruction. This can be really handy if you say, well, I know that the first 5 lines of my program are good, but there's something happening somewhere between line 6 and line 10, and I need to take a look at it. Well, you can use a breakpoint to jump to that point, so the program just runs until it hits breakpoint. Then you can do the stepping to walk through the program. Again, checks the overall results at specific points program, lets you execute sequences to get high-level overview of execution behavior, and quickly execute sequences that you believe are correct. And lastly, we have watch points. This tells the simulator to stop when a register or memory location changes or when it equals a specific value. So if you know it's going to hit like the value 0, you can tell it to stop. This is also very useful when you don't know where or when a value might have changed. So this is more when you're looking at values, you can use this. And that concludes our notes, folks. Until next time.